A formal good evening to all of you. So this is just a ready reckoner for all of you. Not necessary, but just that the different the variables that appear in the Bohr model, okay, such as radius, velocity, momentum, all those things are there, and the ratio of formula for the hydrogen atom, that is Bohr radius 1, radius 2, radius 3. Okay, so in what ratios they are there. So this chart is simply a ready reckoner for all of you. Nothing to teach here. Okay, it's just that all the things are there. Of course, orbital current, those things I will teach you. What it means. Potential energy, I think all these formulas or all these physical variables are known to you, right? Hello, please answer.
Yeah.
Do you know what is orbital current? Hello.
Yes,
What is orbital current? First, orbital current. What is it?
We don't know, sir.
Anybody can guess it?
Sir, the current produced when an electron revolves in an orbit.
Excellent, excellent. That's all. See, now here, what is the concept of current? If you quickly tell me, then I can quickly summarize it and go on. Go ahead. What is the concept of current? Electric current.
Time rate of flow of net charge.
Excellent. Time rate of flow of net charges. Correct? So, in mathematical model, time rate of flow of net charges, time rate of flow of net discharges. Okay? So, or I'll write it as I is equal to, or I'll write it as I of t is equal to dq by dt.
Yes, sir.
Okay. So, here Q stands for what? Net discharges.
Yes, sir.
Net charges. Okay. Net charges means, so if you take a given volume or a given area, right, or a given point also, then you should take the positive charges. Okay, say there are n1 number of positive charges and n2 number of negative charges. Okay, so you have to physically add them. Okay, physically, arithmetically add. Then what we get here is the net charge. I suppose you got this.
Yes.
That means now you see, if there are n1 number of positive charges and n2 is also equal to n1. So in a given volume, though you have got both positive charges and negative charges, the net charge in that volume is 0. I suppose you got it.
Yes, sir.
So now, what is the net charge of this body? See, this body, if I take, it has got both protons and electrons. Correct?
Yes, sir.
So what is the net charge here? 0. Got it? That's all. So the concept of net charge is this. So what it means is, if you are considering an area like this, or a point here in space, area or point in space. Now charges are moving. Okay, charges are moving from here to here. Continuously charges are moving across this area or the point. Okay, now assuming that the electrons are moving like this, okay, and the positive charges are moving like this. Electrons are moving like this and positive charges are moving like this. So at this point, simultaneously both of them are moving. So at any given instant of time, so if you say n number of negative charges are moving and simultaneously n number of positive charges are moving at this point. Okay. Now, what is the electric current at this point?
Zero.
Okay. Anybody else? Okay, nobody is answering. It's not 0. It's a decision, it is not 0. See here, the electrons are moving like this. The negative charges are moving like this. Okay, negative charges are moving in this direction. Okay, then conventionally, see the current is convention. What is the convention current? Negative charges are moving like this. Then the conventional current is in this direction. Okay?
Yes, sir. Yes.
However, if positive charges are moving in this direction, then the conventional current is in this direction.
High potential to low potential.
High potential to low potential. Now don't bring all those things like that here. When I am talking this, no, don't bring any potential at all here. Okay? It's a very concentrated concept. I'll get back to it. So right now you see if electrons are moving in this direction, then the conventional current is in this direction. If the positive charges are going like this, then the current due to the positive charges are in this direction. Now here what happens? The electrons are moving like this. Conventionally the electron current is in this direction. But the positive charges are moving like this. So the conventional current for positive charges are like this. Is that clear? So therefore there is net current flowing at this point. So this, what is it now here? This plus this, if you add, you will get the net current I flowing at this point. Okay. However, if you take some area here, if n number of electrons, negative charges are going like this, and n number of positive charges are going in this direction, then you see due to the negative charges, the current will be in this direction. Due to the positive charges, the current will be in this direction. And since both of them are n, so the net current passing through this point is 0. Is it clear?
Yes.
That is what you have to see. Okay. So in our case, so the current is like this, and this is how the current concept of current has to be understood. Now in this case of electron, see, an electron is revolving. Electron is negative charge and it is revolving. Okay. Now according to this definition, you set your eye at any point. Say you set your eye at this point. So here you will find that the electron will pass through this point and again come back here, again come back here. That means the electron will pass through this point in time t. What is t? The time period. The electron will go from here to here to here. That is one time period. I suppose you got it. Say yes or no. Everybody there. Don't keep quiet. So that is it. So now according to this, E by T, charge by the time to which it is flowing. This gives you the current, electron current flowing. Okay, and that is precisely what you see. Orbital current. That's what you see. Okay.
Yes.
Fine. So angular momentum. Angular momentum already we have discussed this. NH by 2 pi, etc. Okay. Potential energy also discussed. We have discussed this one. This is just a ready reckoner for all of you. Anytime you can refer this. See all this at the end the abstraction is readily made so that when you are going to revise this portion, very important, then these charts will become very, very handy to all of you. Okay. Now these are all the formulas which we have already used. However, I have made a mention of this. See, this formula already we have used. Okay, so only thing is I have once again put this poster here only because the number, what is this? Wave number is equal to, we have the tradition of writing it as R into bracket 1 upon n1 square minus n2 square, and this formula is also referred to as Rydberg formula. Okay, yes. Because somewhere down the line and this needs to be known that this formula is known as this format is known as Rydberg's formula. And one more important note is here is an energy of one Rydberg. An energy of one Rydberg. See, this is also a unit of energy. Means 13.6 electron volt. Okay, because in some numerical they have used this as the energy. Okay, energy of the Rydberg energy. It is useful to remember that R into Hc, okay, is equal to 13.6 electron volt, and Hc is equal to 1242 electron volt nanometer.
Yes, yes.
Okay, so this is a very useful formulation. As I told you in the last class also, the examiners can play around you with the units. That is, if they want to create a lot of interest in the problem, or if they want to complicate it, if they want to really twist it, so one of the ways to twist it is in this units. Okay, 1 Rydberg means 13.6 electron volt. Rydberg into Hc is equal to 13.6 electron volt, and Hc is equal to 1242 electron volt nanometer. Okay.
Sir, can you please explain how dimensionally RHC is?
You please check it out. You please check it out. No, you please check it out. Please check it out. Huh? Please check it out. And if you have issues there, you let me know in the next class. Okay.
Sir, because we the one which we had, Sir, Rydberg constant, that was per meter or per centimeter, and here HC they have given electron volt nanometer.
That's what gentlemen, you just check it out. Just check it out. Huh? Check it out. See, because you see, energy is what? Energy is NH by 2 pi. Correct? So, energy is what? H nu, and it is Hc by lambda, isn't it? Hc by lambda is electron volt. Do you agree?
Yes, sir.
So Hc by lambda is electron volt. So if you shift the lambda to the right, then you have to write the units of lambda, and the units of lambda will be in meters. In this case, it is nanometers. Why it is nanometers here? If you express Hc as 1242, yesterday I told you, then that means now you are expressing the energy in terms of electron volt and the wavelength in terms of nanometers. Got it? That's it. Anyway, I have a numerical on this that will make that aspect very, very clear. Then, this is also known to all of, I suppose all of you know this.
Yes,
this is something which all of you would have enjoyed in the class. Okay? Spectral lines of hydrogen atom. Anyways, I am showing this chart because of some sentences that is very important here. Some sentences are, the excited state is unstable. An electron is made to jump from lower orbit to higher orbit. Then we say it is excited. The excited state is unstable. Hence, the electron returned to the ground in approximately 10 to the power of minus 8 seconds. Okay, so you make an electron to jump to its higher state. It will not stay in the higher state forever. It just stay there for approximately 10 to the power of minus 8 seconds, and because of the pull of the nucleus, that electron will automatically jump back to its ground position. Right? The excess of the energy is now radiated in the form of radiations. That's what we have seen, the photon radiation that happens. Different wavelengths constitute different spectral lengths, and therefore, again, back to this, wave number is equal to 1 by lambda is equal to R into 1 upon n1 square minus 1 upon n2 square. Okay, this relation expresses the complete spectrum of hydrogen detailed. So you know Lyman series, right? So in this formula, if you put n1 is equal to 1 and n2, you put it as 2, 3, 4, 5 here, then you go on getting the spectral lines. Okay, so first member, second member, so on and so forth, and the limiting is when the electron is made to jump from infinity to this first position, whatever you get. The most important thing is here you see the Lyman series. It is going to emit the photo energy in the form of photon, and on the spectral on the spectrum you are going to see this the electromagnetic radiation in the ultraviolet region. So you know the spectrum, right? You will have the infrared, visible, then ultraviolet, then X-ray, gamma rays. So it will be seen in the ultraviolet region, right? Then similarly the Balmer series. So here you see the first, this one here it will be 2, and then 3, 4, 5, 6. I suppose all of you know this. See, newcomers, Sana, Saurabh, Prabhu.
Yes, sir.
Yes, sir.
Right. So, so this is the Balmer series. Okay, and again this series lies in the visible and near ultra region. Visible and near ultra region. So this is something that all of you should remember, because these are the points where they can coin a question or two on this. Similarly, you have this being 3. Okay, N1 being 3, N2 being 4, 5, 6, 7. So they are called the Paschen series. Similarly, you have got the bracket series and so on and so forth. So the most important thing is this Paschen series will lie in the infrared region, and the bracket series will also lie in the infrared region. Infrared region is what? Just before the visible region. P-bond series are also in the infrared region. right? And this is the summary of all of them. So that should make things very, very simple and clear. So all this, whatever we have written, it is put into a nutshell here, right? And then, of course, the what is this called? This is called energy level diagram. Okay, right? This is also known to you. So in the theory examinations, they can ask you what is the energy level diagram and all. So here, mentioning this 13.6 minus 13.6 is very important. And then you see the energy levels. As you can see, the magnitude is decreasing, but the value goes on increasing as you go from down to top. That means the energy is increasing.
Yes.
Okay, and therefore it is very clear. Lyman, Balmer, Ascham, bracket, and default series. Fine, all these things you have studied in detail in chemistry, and I am sure that all of you are excited with these things because it is easy to comprehend. Okay, now in the energy level diagram, what is most important is in the theoretical examinations or otherwise understanding, these lines are representing what? These lines are representing the total energy. That is what is important, not just the energy. Okay, because the energy at each level has two components. One is the potential energy, other one is the kinetic energy. So that is why this word total energy is to be used, and try to keep using this word stationary orbits. What is it? Stationary orbits. Okay, why we are using the word stationary orbits? Because in those orbits, the electrons are moving, and even though they are accelerating, they are not radiating energy.
Radiating energy, yes.
That is why this concept of stationary orbits is being used. And another reason why this word stationary orbit is being used is because now when we convert the electron into a wave nature, that is a wave function, and when you represent the wave function of the electron, then you will find the standing wave pattern of the wave. The electron can be represented as the standing wave, and you know what is a standing wave, right? So standing wave in a wave is a wave, but it is not what?
Transmitting energy.
Yes, it is not propagating the energy. Right? It is not propagating the energy. So that is the idea. So when you want to look at the electron as a wave, right? Then along the orbitals you can draw the standing wave pattern, and those standing wave patterns are the stationary waves. So this name stationary has been coined for that reason. Okay, so that was the important abstraction from this paragraph. That's what I think. I think all of you know this. E1 is so and so, E2, how you got this 13.6, this one. As you know, E is directly proportional to, inversely proportional to 1 upon N square. And therefore, N goes on increasing, so you can get these values. To take an electron to infinity from level 1, N is equal to 1, an energy of 13.6 electron volt has to be supplied to the atom. E1 is equal to 13.6 electron volt, also called binding energy in orbit N is equal to 1. Okay, so I have marked this because this is one of the probable questions which already has not probably, it has already been asked in various examinations. But see here, binding energy in orbit N is equal to 1. So now when you see multi-level electrons, then the electron in the next level will have certain energy, and that becomes the binding energy at that level.
Yes, sir.
Okay, very important. Okay, so because they had asked a question, what is the binding energy of electron in the first orbit? So if you don't know the concept, what is binding energy, then you don't know. It is very simple. So that's why I have highlighted those aspects. Anyway, I think this is...
Excuse me, sir.
Yes, please.
Sir, after we provide 13.6 electron volts, it will jump to, like the electron excites and jump to infinity, sir. Then again, will it after 10 raised to minus 8 seconds, again will it?
No. Thank you for this one. See, what is the thing is, see, now the electrostatic force. You remember? I told you electrostatic force. Okay? I hope you remember, gentlemen. So the electrostatic force is what? Q1 into Q2 divided by R square. Okay? This is K into so much. You remember? Okay?
Yes, sir. Yes, sir.
Now you see, as that means that electrostatic force goes on decreasing with the increase in radius. So if you have taken the electron to infinity, then what is the force which will make it to bring it back? There is no force to bring it back. So it will never return back to its ground state. Okay? Okay, that you can mark it as an exception. See, that is why if you make the electron to jump to the orbits, that is n is equal to 1, n is equal to 2, n is equal to 3, then it will come back. But for n is equal to infinity, no, it will not come back. Okay, it is like in gravitation, you use the concept of escape velocity, right? So if
Yes.
you throw a body with escape velocity, that is on Earth, it is 11.2 kilometers per second, then the body will never return back to Earth. So we say it has escaped the gravitational force of the Earth. Similarly, if you provide this potential, then the electron will move out of the atom and it will never return back.
Okay, sir.
Right. Now here there is one more data. Now here excitation energy and excitation potential. So I have marked all these things separately because there are explicit questions to differentiate these two, and now I have brought it to the fore. Of course, all of you know what is excitation. That is, the electron absorbs the energy from external source and will jump from the inner orbit to the outer orbit of higher energy. This process is called excitation, not from higher to lower. Okay. Excitation energy required to raise an electron from ground state to the first excited state N2 is equal to so and so. So E excitation is minus 3.4 minus of minus 13.6 is 10.2 electron volts. That means if you provide 10.2 electron volts of energy to the electron in its ground state, then it will jump to the next state. Now here close to it there is excitation potential. So V stands for excitation, V stands for potential, and V suffix subscript excitation stands for the excitation potential. Now what it means is how do they actually cause the excitation? So they take the say for example they take hydrogen gas between the two cathode ray tubes, hydrogen gas, and they increase the potential difference between the two cathode ray tube between the two plates to 13.6 volts. Okay, then here 10.2 volts. Then you can say that the electrons are now most of the electrons of the hydrogen atoms present there, they will get excited and they are all in the n is equal to 2 state. So this is the excitation potential, excitation energy, excitation potential. This one more note is important. Excitation potential of an atom in general can have infinite values. Okay, so this is also important because it will depend upon where is the electron, at what point is the electron, and from there onwards you have to excite it. That is, if the electron is in the first orbit, then you have to provide so much amount of energy to excite it to the next level. But if it is already in the second level and if you want to cause the excitation, then you have to take that level into consideration. So in that context, it can have infinite values depending upon the state in which it is excited from the ground state. Okay, so there was a question, what are the how many values can it take? It can take infinite values, depend upon the position of the electron from the nucleus, from which orbit it is there.
The value can be infinite, or there are different infinite values.
What do you mean? What is the difference? Infinite values means?
Sir, infinite value means the excitation, the potential need to be provided should be infinity, sir.
No. Potential need not be given infinity. Okay. See, now if the electron is in n is equal to 1 state, then there is and if you want to push it to say n is equal to 5, then you have to provide certain amount of energy. If the electron is already in n is equal to 2 state, then if you want to push it to n is equal to 5, then you have to provide the difference of that energy.
Okay, sir.
So like that, the n can have values 1, 2, 3, 4 to almost infinity, but not inclusive, not including infinity, right? N values are finite. N values are finite, but they will extend till infinity, but not equal to infinity.
Okay.
Now, close to this excitation energy, you have got ionization energy. So, as you know, the most important thing is large enough to knock off an electron from the outermost orbit. That is important. And in fact, something is missing here. As one of your friends yesterday said, it is the energy necessary to knock off an electron in the gaseous state.
Isolated.
Isolated.
Yes.
Isolated gaseous state from the outermost orbit.
Yes, sir. Yes, sir.
Then, the other word is the minimum accelerating potential with which to provide the electron energy sufficient to just remove it from the atom is called ionization potential. So, why I am marked it, highlighted this is because these words, the minimum accelerating potential. Accelerating potential is, yesterday I showed you, one negative plate and one positive plate connected to a battery. So then you are providing the potential difference between these two plates, and if you keep an electron here and if this is a positive plate, then due to the electric field, this electron keeps on accelerating. And that is why the potential difference here is called accelerating potential, which should provide an electron sufficient energy to remove it from the atom, and it is called ionization potential. So the word here is minimum accelerating potential, which would provide an electron energy sufficient to remove it. That is important. Minimum accelerating potential. Okay, that's why I had marked it. And of course, we used to write here E is equal to 13.6 Z square by N square. As you have already seen here, ionization energy is 13.6 electron volt and ionization potential is 13.6 volts, because you are providing this to knock off only one electron. Okay, so therefore this is how we are going to end up. Fine, shall I proceed?
Yes. Yes.
All this you have studied, so therefore I am quickly running it through. I have got one more abstraction here, same as what was written above. I just highlighted, I'll just go through the highlighted things. So, unexcited or normal state. That means now, when an atom is formed and no external energy is given to it, all the electrons are in its normal state. And here we are referring to hydrogen atom, so therefore it has only one electron. So, if the electron is in at the position n is equal to 1, then we say it is unexcited or normal state. When an atom is in a state of high energy, we say atom is in a state of high energy. What does it mean? State of high energy is said to be excited. That means if the electron in the atom is excited, then we say it is in a state of high energy. Okay.
Yes.
Now the atom left its position. So the process of raising an atom from normal state to the ionized state is called ionization. Another golden sentence here. What is ionization? Of course, the definition already we have gone through. Now another definition for this is ionization is a process of raising the atom from its normal state to the ionized state. So normal state and ionized state is also called ionization. The process of excitation, ionization are both absorption phenomena. See, all the sentences that I have abstracted are questions asked in examinations. Okay, so they are picked from some corner, from some textbook, and then a question is coined. So I have tried to gather a lot of question papers and abstract it, and I am putting them in the form of sentences. The process of excitation and ionization both are absorption phenomena. The excited state is not a stationary state, and it lasts for very short interval time. And because electron is under active attractive force of the nucleus, jumps back to the lower part of it. Okay, fine. So there is questions on whether this assertion is right and the reason right. So in that this has appeared. One more word that has come here is resonance potential. Okay, right. The minimum potential we require to accelerator. See here, an electron can be excited by providing energy to the electron, there are several ways of providing energy to the electron. One familiar way is for the electron, if a photon comes and hits the electron, this photon energy is absorbed by the electron and it excites. That is one thing that we are all familiar. The other thing is this. One of the other things. What is it? The most commonly thing is kinetic energy wholly or partially of an electron. That is, they make an electron to travel at very high speeds, and this high speed electron, as it's traveling, when it hits the electron in an atom, there is a free electron traveling. If it hits the electron of the atom as it is traveling, then that electron and the fast moving electron, the electron in the atom and the external electron, they collide, and this collision results in increasing the kinetic energy of the electron of which is a part of the atom. And therefore what happens? So this is called bombarding the electron from a fast moving electron. So the atom is now in excited condition. The minimum potential V required to accelerate the bombarding electrons to cause excitation from ground state is called resonance potential. Hello?
Yes, sir.
So now there is one more question. Where do you find this familiar? See, in tube light. How does the tube light work? There is a coating of the fluorescent coating is there. So here, when you switch on the tube light, there is something called choke. I'll explain all this when I teach you electricity. So at the choke, even though you are providing 240 volts potential, 240 volts AC potential to the tube light, it develops approximately 1000 volts potential difference for a short duration. This 1000 volts potential difference between the ends of the tube is so high that it starts accelerating some free electrons, and these free electrons start accelerating from this side to this side, and in the process they ionize the gas inside the tube light, and therefore more and more ions are generated, more and more free electrons are generated, and they hit the screen, the fluorescent screen. Their kinetic energy is converted into photo energy. That is how the electrical energy is getting converted into the light energy. Okay?
Yes.
So the minimum potential to cause the bombardment is called resonance potential. Okay, right, that is one thing. Then there is another term called critical potential. The term critical potential is used to include resonance, excitation and ionization potential. All of them put together, they use the word critical potential. Okay, these are some things, some information that all of you know, because they are asked, because there are textbooks which the students have to refer, but you don't have time to refer many textbooks. So obviously in one textbook they would have given some information, another textbook another information, but anyways I have tried to collect all of them and put it across. Okay friends, shall I move on?
Yes.
Now
Sir, one doubt regarding ionization potential, sir. Sir, ionization potential is defined for an atom in gaseous state, sir. Sir, and like for an atom, sir, how can we define a gaseous state, sir? Means one atom means it is either.
See, the theories, the definition is like that. That is, supposing you say, you take any element, you have to first convert that element, if it is in solid state, to gaseous state. And in that state, you have got to isolate an atom. And then you have to give sufficient potential so that the electron from the outermost shell goes out. Now I am telling you, friend, that is how the definition is. But what happens is, when you want to apply it to a particular element which is also in the solid state, etc., then there are certain modifications to that formula. Okay, so the science develops for that. That is not for you, because you are going to learn a lot more chemistry in BSc, MSc and all. So there you will have the formulations for that. At this stage, this is what is to begin with. Okay?
Yes. Sir, and Sir, and how will ionization potential vary with gaseous state or liquid state or solid state?
That's what I told gentlemen. See, here we are beginning to understand this concept of ionization. We are beginning. It's not complete. That completeness will come only in your higher studies. Right
Yes.
now, you should be satisfied with this. Okay?
Yes.
That's how it is. Because you see, science is developed like that. See, in high school, we only said a particle will move along a straight line and we derived the equation V is equal to U plus AT without even referring to vectors. But now you know when if the acceleration is not constant, then you can't use the formula V is equal to U plus AT. So you have to go for differential equation, etc. So on and so forth. So you see, the stages of learning will be like that. Fine.
Yes.
Now, a small note of success and limitations of the Bohr, Bohr model. Bohr showed that Planck's constant quantum ideas were necessary element of an atomic theory. He introduced the idea of quantization energy levels and explained the emission or absorption of radiation as being due to transition of an electron from one level to another. As a model for even multi-electron atoms. So in chemistry you will learn this. That is the yes, already you have learned. So what you have learned for hydrogen-like atoms, you can extend it to multi-electron system. That is, you are going to apply the Bohr theory for even lithium. So what did you do there? You knocked off 2 electrons and lithium now becomes a hydrogen-like atom. So that's what is it. And even if you know knocked down also, the theory that is developed for multi-electron system is advanced from the basic model of Bohr. As a model for even multi-electron system, the Bohr picture is still useful. It leads to a good example, rational ordering of the electron in larger atoms, and quantitatively helps us to predict a great deal about chemical behavior and spectral data. So this is something nicely said about Bohr. Now coming to the limitations. The Bohr theory is unable to explain the following facts. The spectral lines of hydrogen atom are not single lines, but one is a collection of several closely spaced lines.
Yes, sir, doublets.
Yes, sir.
Okay, so that is like this. So supposing you see a thread, you will see only a thread. But if you come very close and look at the thread itself is made of many threads.
Yes.
Okay, so like that, those spectral lines, Lyman, Bohr, all those spectral lines, if you subject it to external magnetic field, you will start seeing that each line consists of many lines.
Yes, sir.
Okay, and closely spaced lines. What did you call, Mr. Sijan? Some name you said?
Doublets.
Doublets. So what is it due to the lines?
So like when we use in chemistry, sir, we learned that if we use instruments which have higher resolution, sir, we'll be able to observe doublets, sir, and that is due to additional energy levels, additional and vibrational energy levels.
What are those energy levels? Sub-energy levels.
Yes, sir. Subshells and further.
Yes, that is because the orbits consist of sub-energy levels called orbitals.
Orbitals, yes.
Orbitals are sub-energy levels.
Yes.
Right. The structure of multi-electron atoms is not explained using the Bohr theory, because by the time Bohr theory could not explain why there will be line by line. Okay. No explanation for using the principles of quantization of angular momentum. I think one of you asked, I think Mr. Ligade asked. So, because I explained the first one, that is the centripetal force was related to, the centripetal force was related to the electrostatic force. And the second postulate is the angular momentum will be equal to nh by 2 pi. And I think one of you asked, I think Mr. Ligade, am I right? Sir, how did he confirm that angular momentum is equal to nh by 2 pi? Okay,
Yes.
that is one of the limitations. No explanation for using the principle of quantization of angular momentum. No explanation for Zeeman effect. If a substance which gives line emission spectrum, as we have seen now, is placed in a magnetic field, the lines of spectrum get split into number of closely spaced lines. This phenomena is called as Zeeman effect. Okay, so these things could not be explained by Mr. Bohr.
And also stack effects.
Yes, electric field.
Yes, sir.
Yes, those see electromagnetic effects, are not explained by this Bohr theory.
Yes, sir.
Fine, students. Okay, so you see, to a very great extent, I have covered the theory portion for the atomic structure. But the chapter doesn't end here. You have got X-rays, photoelectric effect, etc. All those things. Anyway, I will teach all of them. After you write your examinations. We will examine some very good numericals. I think I said I have sent some numericals.